I would like to express that I'm very happy that this QCrypt, or in particular this sheep, gained a lot of speed in the last few years, and it's nice to see how this conference grows and is successful. And I would like to thank the organizers of also the previous conferences, also the one in Waterloo that we saw last year, organized by Vadim, and of course the organizers of this year's conference for taking the effort of making this a successful event. I would also like to stress that this is now a tutorial, and I decided to do it on the whiteboard. The idea is that this leaves me more room to be interactive and to actually take questions. So I strongly encourage you to ask questions whenever there are any. There's enough time, and I'm very happy to also skip certain material at the benefit of going into the more detailed answers. Then I would like, because this is a talk on finite size or quantifying security, I would like to stress that this is not supposed to be a tutorial for the specialists who work daily on this topic. It's rather meant to be a tutorial for those who are not dealing with that every day, but they are in they have to care about it because maybe they are building QKD systems. So it's supposed to be a tutorial for all those who have heard about quantitative security but don't know exactly what it is, or maybe they don't know what it exactly is and want to know a little bit more. But it's not just a tutorial for the specialists. And the things I'm going to present are based on works by many people, and I will not be able to acknowledge all of them, but I would like to thank particularly Valerio Scarani, who was one of the persons who initiated this whole field of what is sometimes called finite size security. Okay, so the idea of this tutorial, or the structure, will essentially be that it consists of 4 parts. And the 4 parts are essentially 4 questions. So I would like first to ask the question, why? Why do we need to care about what I call quantitative security? Then I will, of course, tell you what it means. So this will be an important big part of this tutorial. What does it mean to quantify security? What do we actually quantify? Then, of course, this will be like a more detailed part about how do we do it? What do we need to do in order to make quantitative security statements? And then I will also give a brief outlook, and I could phrase that also as a question, what next? What do we need to do in order to make progress in this whole field of QKD? So let me start with this first and maybe most important question. Why should you be interested in quantitative security? And one of the maybe most important messages that I should give right at the beginning is that without quantifying security, we cannot really make a scientific statement. So if I make the statement about the quantum key distribution system and say, this system is secure, then this is certainly a statement that somehow makes sense to, let's say, someone who wants to buy, to a customer, but it's not a scientific statement. So let me write this statement, so because I will then change it. So this QKD system is secure. So I don't want to claim that this is a wrong statement, but it's just not something I can scientifically verify. It's not a clean statement. In order to illustrate everything that I'm going to talk about, it's usually very useful to think about other fields of engineering. And one typical example is if you look at an engineer who designs an aircraft, then he, of course, at the end wants to make the claim that this airplane that he designed is secure. But again, if he just makes the claim that this airplane that I designed is secure, then what does that mean? I mean, clearly we see sometimes airplane crashes, so it cannot be that there is an absolutely secure airplane, but still there is something contained in this statement. It's not an empty statement. And the idea to resolve this is to actually give some parameter of how secure it is. I mean, essentially the reason why I'm saying this cannot be a scientifically correct statement is that we will never achieve something that is absolutely secure. There is always a certain probability of failure. And if I don't state this probability of failure, then the statement cannot really be evaluated. So what would be, I mean, maybe I write that here. So we have the equivalent statement like this airplane is secure. That would be, or does not crash, for example. So what would be a more precise statement here? Oh, thank you. So a more precise statement here would be that some statement potentially about some probability. So what one may say is that the probability, okay, this is not really the probability that this pen doesn't work is also bad, but okay. The probability, and now I make two changes. So first of all, I introduce probability that this plane crashes. And then I say something, I have to say something about the assumptions. For example, I could say assume that there is no human failure. So I could say due to technical failure is at most some value which I call epsilon. So this is something we would like to achieve also in cryptography. It's clear that this statement is much more useful. And by the way, here these numbers are actually calculated. You could, by the way, kind of take two different approaches to calculate the number. You can either look at the airplane and then analyze it, take the components apart and try to come up with this failure probability, or you can just make tests. You can just fly with many airplanes and calculate how many crash. And that's, of course, what's happening in reality, and this is how we get this number. So in reality, we know that the epsilon on this side is essentially 10 to the minus 7 to 10 to the minus 6, depending on the airline, per flight. So this is an empirical number, but it's a clear number. Now it's a very clear statement. Now, I mean, if someone says flying airplanes is safe, then this is just his estimate of how he sees this number epsilon, to what he compares it with, and so on. And you see that with that statement that is just not captured. It's not clear whether this kind of statistical statement is now captured by this first thing. So what we want to achieve, and that's what is quantitative security, is essentially to make a similar statement about QKD systems. That's the goal. So that's just to maybe motivate the whole thing. And you see probably from comparing this blue statement with the black one that the blue one alone doesn't really make sense in some way. So in other words, what we want to say here is that we want to have a statement of the type, this QKD system will fail. And I will, of course, tell you what fail means. With probability at most epsilon. And here also, as in the same way as I said here, due to technical failure, I could say here, I have to be here a little bit more general, provided certain assumptions hold. And the assumptions will, of course, be assumptions about, for example, what are the constraints about the adversary, what is the adversary allowed to do, and so on. So this is the type of statement we would like to obtain. And I hope that this little introduction answers essentially the question why. So you should be convinced that whatever you do in practice, whenever you build a system, you need a statement like this in order to actually say something useful about the system that a customer or client can actually use to assess whether he wants to use it or not. Okay, so now one question that one may immediately ask is that, what if epsilon is 0? If it was possible to design a QKD system such that epsilon is 0, then we could again return to this statement and say this is actually what we meant. And there is kind of a misconception among some people to say, isn't it proved that QKDs are information theoretically secure? And doesn't this mean that actually epsilon is 0? So this is not the case. And just to illustrate this, you know that, how do I? So if you even take the I mean, this is kind of a trivial statement, but I need to kind of make it at some point. Even if you take a very simple, conceptually simple QKD system, let's say with qubits, a very clean system, for example, the BB84 protocol, then you see that at some point we make a choice between two bases. We encode information either in the rectilinear or computational basis or in the diagonal basis, and we send information or random bits encoding these two bases over the insecure channel. Now, an adversary could in principle apply an attack where he always tries to guess which basis has been used. And if he guesses correctly, he could kind of copy the information in that basis, and as soon as the basis, of course, is known, you can copy information without destroying it. So as soon as he knows the basis, he can actually steal the information without being noticed. Now, for each bit that is sent from Alice to Bob, Eve has a probability of guessing correctly of 1/2. And of course, the probability of always guessing correctly decreases exponentially fast, but it will never reach 0. So the probability, so this is like n times we do that, and then the probability of guessing correctly is epsilon 2 to the minus n. So this gives you a very bad, by the way, but it gives you a lower bound on how much security you can potentially achieve. So everyone who claims that he has a QKD system which achieves a value which is smaller than that is almost certainly wrong. Of course, I didn't now make a provable statement, so maybe someone comes up with a more clever QKD system, but the statement is quite generic, because one could say that any known QKD protocol has something like a parameter estimation phase, which consists of kind of a step in the protocol where you try to estimate to what extent the adversary influenced the channel. And in order to carry out this estimation, you need to do certain random measurements in random basis. And if the adversary knows this randomness, then he could always adapt the attack in such a way that it's successful. So in other words, although the adversary doesn't know this randomness, he could guess it with a certain probability, and this guessing probability will always be of that order. So in other words, it's not possible to hope that this epsilon will ever be reach the value 0. In the same way as we cannot hope to ever design an aircraft which will fly, which will not have a technical failure with probability 0. Because, simply for thermodynamic reasons, every material has a certain probability of falling apart. So in other words, we are forced also to make such more precise statements. Okay, so this concludes my very first part, kind of the motivation of everything. Why do we need that? And I hope I convinced you that it's absolutely necessary. There is no way around that. A security proof on this level doesn't just work in some way. Okay, if not, then I will proceed with what does this now mean? And I hope this will also partially answer this question that Christoph Pacher asked about what is, for example, guessing a key a failure of the crypto system. So in order to do that, I would like to first start with an observation that something you have to expect is that, of course, we can now choose our parameters of the system, and we have seen specific numbers in the previous talk. And actually, the previous talk was a very good example of someone who really takes care of stating the epsilons correctly. Because one thing you first of all have to be aware of is that in the same way as for this failure that I gave there for the crash, the failure is always it's always a rate. For example, here it's the probability of a crash per flight. And of course, if you take an airplane every day, your probability of crashing is higher than someone who only flies once in his life. And in the same way, the epsilon here is not just a probability, it's actually a probability per, for example, use of the QKD system or per bit that we generate. As a designer of the system, you can choose how you exactly state the rate, but you always have to be aware it's a rate. And of course, the final probability of seeing a failure will be the times, for example, you use the crypto system times this rate of failure. And so expect there to be a rate. The other thing you have to be aware of is that there will be a trade-off. Of course, we want this epsilon to be as small as possible. And it's also clear in the airplane example that there is a clear trade-off. You could, for example, decide to have no redundancy in your aircraft. You just have one navigation system and you have only one engine and so on. And then, of course, the probability of failure is larger, but the costs are lower because the aircraft is lighter and so on. And the same is true for QKD. You can essentially choose how large you want to have your epsilon. And usually what you will see is a dependency of the following type. This is now a very rough graph, but you have here the costs. And the costs are essentially, for example, how many signals do you have to exchange in order to establish your key? And this is, of course, also will influence your speed and so on of the system. So costs is kind of the cost per bit, also time cost. And here you have the security. And the security I could, for example, measure, it's reasonable to take something like log 1 over epsilon as a good measure, because the larger this number then is, the better is my security. It's essentially the exponent. Do I want to have 10 to the minus 6 or 10 to the minus 7? And you have to see that the curve is a growing curve. It's maybe not linear. It depends on how you calculate the cost, but it's this curve, and there is a trade-off. So you want to find, you have a certain level of security you want to achieve, and then you have, of course, a certain amount of cost that is needed in order to reach that point. So that's something you have to be aware of when we talk about this epsilon. So at the end, there is no number. I will never give you a specific number what the epsilon is. It's just you can essentially make it arbitrarily small or make the security arbitrarily high, never zero, or never. This value can never be infinite. And it's just a matter of how much you invest. And so let's now see that what that now means. Because now in order to choose what value we should take here, we need to understand what a failure means. Okay. And let's compare the whole thing again to the thing here. So I think on the right-hand side, everyone understands immediately what is meant by a crash somehow. Of course, you could still debate whether crash now means that whether you die or not, and actually this probability here is defined by the probability that you die during the flight due to a crash. And now the question is, what does a failure mean for a QKD system? There's now one important conceptual difference. On the right-hand side, it's kind of obvious whether you fail. As a customer of an aircraft, you will probably notice, or at least, maybe you, I don't know whether you notice if you die, but you in principle notice whether the whole thing fails. Whereas in QKD, you usually wouldn't notice if an adversary manages to read your key. Maybe you notice later if you can exploit this fact, but you don't notice. And this is the thing that makes the left-hand side much harder to define than the right-hand side, because a priori there is no failure event, so to speak. So we have to, nevertheless, we have an intuitive understanding, first of all, what failure means. So what could failure mean in this case? And let me maybe start with this intuitive picture and then make it precise. So a failure could mean that the adversary learns the entire key. That's one possibility. However, that's probably not, that would not be sufficient to define our security, because failure could also mean that the adversary learns something, for example, 1 bit of our key. So that could be another type of failure. Or it could also be that the key of the two parties, of Alice and Bob, or the keys of them are not identical. That's another possible failure. But that's similar to an aircraft. So if I just say, what is the failure of an aircraft? Then I could also say, if, for example, the air conditioning system fails, the aircraft somehow failed in some way. But of course, this is an error that doesn't hurt me so much as a crash. So I could also say here that this third possibility is not as bad as the first one, because Alice and Bob may later compare their keys and find that out, whereas this they can never find out whether the adversary, or potentially never find out whether the adversary learned their key. Towards the end, I will kind of argue that it will be useful to distinguish different types of failure. But for the moment, in order to proceed, let's just say that we take kind of a more simple approach, which is the usual approach taken today, which says that every deviation from what we actually would expect the system to do should be called a failure. So all of these three things would actually be a failure. So that's the first idea. And as I said, this is just a first approach. How do we now realize this approach? What does that mean, that we have any of these failures? How do we do that formally? And the idea of doing these things formally is essentially to consider this paradigm of comparing real and ideal systems. This is a paradigm that has been introduced in already some decades ago in classical cryptography. Most famous part of this work is by Fitzman and Weidner about reactive security, and by Rand Canetti, where it is called composable security. And this whole concept has been also generalized to quantum mechanics. There are several people in our community who worked on that. For example, Michael Benor, then Dominique Meyers, then later Dominique Unruh. And I'm currently working together with Uli Maurer and Christopher Portman on these type of questions. And there are many others, so these were just some of the proponents of this kind of theory. So the idea is the following. So we kind of try to model our QKD system. And we have our real QKD system, and the real QKD system will, of course, give an output at Alice and Bob and to Eve. And the idea is to look at it from a more abstract way and say, let's put everything into a box. So in this box is the whole optical fiber. Are the devices of Alice and Bob. But at the end, if we look from outside, there will be a key that is given to Alice, and there will be a key that is given to Bob. And also the adversary gets usually something. So this is some leaked information. Let's call it L. Now, there is some ideal thing, which is the thing we would expect. And by the way, the real thing could also provide the adversary some possibility to influence these keys. So I put here an input E that the adversary could give. The ideal thing that we would like to have is something that just gives out the key to Alice, a key to Bob, and nothing to the adversary. So I always draw the adversary here in the middle. So the idea is that first of all, we want that SA is equal to SB, and we want that the probability distribution of S, or let's write it like that, the probability distribution of S, so because they're identical, I could just call them S, is uniform. So what I'm saying is that we are trying to draw a device, and if we had this device, we would kind of, per definition, be happy. And that's kind of the device. So suppose we have some magic box that we could distribute between Alice and Bob, so it's kind of a huge device. And Alice and Bob just get random bits out of this box which are identical, and there is a guarantee that no one else gets any information about these things. So that's kind of what we would like to have. And that's what we actually have. So we have some device that probably does that, more or less. And the idea is now to say that a failure is essentially the case where this behavior deviates from this behavior here. So that somehow makes sense. You could again do the same thing for an aircraft. So this would be an airplane that always flies and never crashes. And this is one that is real and may crash with a certain probability, or there may be some other failures. And the probability of this aircraft failing is essentially the probability that its behavior deviates from the ideal behavior that we have. This is a kind of generous definition, as you see. So it could be that this aircraft doesn't crash, but in another way deviates from the ideal behavior. As I said before, maybe because the air conditioning doesn't work, and in the ideal one it always works. So in some way, if you have a bound on how much this deviates from that, this bound may be too pessimistic, but we are certainly on the safe side. So it's certainly, if we know that the behavior here doesn't deviate from that, then we are certainly happy. It doesn't, on the other hand, mean that if it deviates from that, we are necessarily unhappy, but that's not so much a problem, because we want, at the end, to be on the safe side. And if we can prove a small probability of deviation, then we will certainly be happy with our statement. Okay. What does this now mean? So first I should say that it's not possible at all to prove that this behavior is close to this behavior. And the reason, under the usual assumptions that we are making in QKD. And the reason is that, of course, what an adversary can always do is to just try to he could just steal all the information that Alice sends to Bob through, for example, an optical fiber, in which case Alice and Bob can never agree on a key. And this is, of course, something that is not possible here, because here the adversary has no way to interact with the system. So this was actually a too optimistic guess that we can reach this ideal system. And usually one has to look at a slightly more relaxed constraint, so I have to kind of change what I call ideal. It would be like, again, in the aircraft thing, if my ideal airplane would be one that flies around the world without a stop, that I cannot reach. It would be nice to have it, but I cannot reach it. And in the same way here, I have to make this thing a little bit weaker. And the way I make it weaker is to say, even for the ideal system, the adversary may give an input E, and I have then the following constraint. This input E could take two values. So the adversary can choose whether he would kind of be passive. So you can say, actually, I leave the system as it is, or he wants to corrupt it. So the adversary has just his choice. I'm passive, I'm nice, or I corrupt it. And now the idea is that this guarantee, the second one, is only guaranteed if E is equal to passive. Now, if I would leave it like that, this would be a completely useless system, because the adversary could always say, I'm corrupted, and then we have no guarantee whatsoever about the key. So we have to add something. And what I add is that SA is equal to SB, is equal to some special symbol, which I call bottom here, if Eve says that she wants to corrupt the system. So if E is equal to corrupt, then Alice and Bob get an output which says, oh, now it was corrupted. So essentially what is the guarantee that I have here? The adversary is free to choose whether he wants to corrupt the system or not, but whenever he corrupts the system, this will necessarily be noticed by Alice and Bob. And that's, when you think about it, really what QKD guarantees. So without the red stuff, this is not what we get. So in QKD, it is true that the adversary can always, in principle, the adversary could always cut the line into two. So it can always make sure that Alice and Bob don't get this key. However, if Eve decides to be passive, then they get it, and whenever she's active, then they at least notice. So that's the ideal thing. That's sometimes called the ideal functionality that corresponds to quantum key distribution. Of course, there are certain things one has to say to make this more precise. I should, for example, say what is the alphabet. I should say these keys are uniform over, for example, strings of length n, or there could be a variable length and so on. But essentially, that's the idea of the whole thing. Now, as I said, what is now the epsilon here? Informally speaking, the epsilon is now the probability of deviation. So what is the probability that this thing is different from that one? Now, how do we measure a probability of deviation? And there is a long debate about that in quantum cryptography by some people, but essentially what this means has already been defined in the classical domain in a very clean and nice way. It's essentially there defined as the probability that you can distinguish from outside. If you would kind of look at this thing from outside, and if you would look at this thing from outside, what is the probability that you see a difference? And I will just make that a little bit more precise. But what is important here is that I stress that it's the difference that you see if you look at the whole thing from outside. So of course, this takes into account that in QKD, one party, Alice, will by herself never be able to notice whether Eve got the key that she produced. However, what I should think of is kind of an outside referee. So I think of some hypothetical referee that stands outside of the whole thing, and he sees everything. He sees what Alice gets, he sees what Eve gets, and this referee can, of course, just judge whether the adversary now got the key of Alice. Alice cannot do that herself, but the outside thing can do that. And this outside referee is in classical cryptography usually called a distinguisher. So the distinguisher is essentially a device that looks at this thing and looks at this thing and tries to see, is there a difference? And then the distinguisher decides whether it's kind of this or that. And how can we make that now a little bit more precise? I would like to illustrate that at a very specific example. So let's assume, because the question is essentially, what does it mean to notice a difference between these two things? Let's just assume that we have a device that generates a key which is not exactly uniform. So let's assume that the real device produces a key which is identical for Alice and Bob. So the first condition would be satisfied. And I draw here the probability distribution of the key. So on this axis are all possible values of the key, and on this axis are the probabilities of the individual keys. So ideally, I would like to have, so this would be, for example, a key sequence consisting only of zeros. This would be the key sequence consisting of only zeros and 1, 1, and so on. So ideally, I want that they all have the same probability. But let's now assume that one particular value of the key appears, for example, twice as often as another one. And let's also assume that there is maybe another value of the key that never appears. So this would be a non-perfect key. So that's kind of the real situation. Now the ideal situation is one where all the keys are by definition, I said here, the ideal one means it's uniform. So by definition, the ideal situation, PS, would be such, let's call that S real, and here S ideal. And so it would essentially look like that. So they have all the same probability. Now, one way to do it, and this is kind of a way some people find useful and others not so much, but I'll nevertheless present it. One way to think about this is to actually imagine that the two devices, the real one, and the ideal one, both exist in parallel. Of course, the ideal one doesn't really exist, but you could imagine that you have your real QKD system, and there is kind of a shadow device that always does exactly the same thing, but it's ideal. So it cannot really always do the same thing, but you would imagine that whenever, for example, the real device outputs a key sequence 0, so if we are here, then the ideal device also outputs a key sequence 0. So they would somehow exist in parallel, and you could always see, are they doing exactly the same thing? Do they again, like for the aircraft, be like one aircraft is the ideal one and the other one is the real one, and they fly in parallel. And now, if one, of course, crashes, you see, of course, difference, but otherwise they would always do the same thing in some way. Now, because this is not an ideal key in this case, sometimes, you cannot set this scenario up that I described in such a way that they're always doing the same thing. Because sometimes this device, this real device, I need to find the red color. Is there some red somewhere? Okay, anyway, it doesn't matter so much. Let's take the blue. I had some red before, but it somehow disappeared. Let's now assume that this particular value here is the one here. So if this appears in the ideal device, then it cannot appear in the real one, because in the real one this has probability 0. But in the real one, this has twice this probability. So I would say, okay, whenever I could set the whole thing up in such a way that whenever this value appears on the ideal device, then this one appears in the real one. And otherwise, they're always doing the same thing. So in some way, you have this green area where whatever happens, in any case, they're really doing identical, they're outputting identical values. So it's not only that they have the same distribution, they're really doing exactly the same thing. Whereas sometimes, in very rare cases, this ideal device will output this value, whereas this one will output that value here, which already occurred in other instances. Okay, so now we have a well-defined event of failure, because the event of failure is just the event that I'm essentially here in this blue area, which, or equivalently this one, depending on what I look at. So I can kind of think of my failure probability of this parameter epsilon, and epsilon would now exactly correspond to that, as essentially the weight of this blue area where the real one doesn't coincide with the ideal one. So that's one illustration of the value epsilon. So in other words, you can really interpret the value epsilon as the probability of the event that the two things deviate from each other. So now we have essentially given a meaning to this value epsilon. And we can now ask ourselves, what is, how do we now bound it? And this will bring us to the next question, how? So I think this ends kind of this section of what do we quantify? So really quantify this probability of deviation from this thing here. And now the question is, how do we do that? How do we come up with an actual value if we get a scheme? But are there any questions regarding the what? Because that's probably the most important part, because here is also the interface. When a theorist who analyzes a QKD system talks to an experimentalist, they probably at some point have to talk, when they talk about the security, about this parameter epsilon. So both the theorist and the experimentalist should understand what they mean by the epsilon. And I hope that what is meant is kind of clear by this picture as the probability of deviation. I should say that I now didn't do that formally, but formally the formal definition follows essentially exactly this idea. There's nothing conceptually different that is added to that. But formally it turns out that this difference will at the end be measured in terms of so-called trace distance, which you know is kind of the probability that you can distinguish two things. Are there questions related to that point? Okay. If not, then I will proceed to the question how, and I just need to check the time. Okay. So how do we calculate the value epsilon? Here comes again a very nice idea that has been developed within classical cryptography, which is the idea of composability, which is kind of has two uses. On the one hand, we can say that composability guarantees that we can actually use this whole thing at the end within a larger context, but composability can also be used to actually decompose the complexity of a QKD system into different parts and then calculate the epsilon of the different parts. So the idea of the how is essentially as follows. So if you have a huge QKD system, then this QKD system, of course, depends on many different parts. I mean, by different parts, I don't necessarily mean different devices, but I also mean different components of the protocol. For example, a QKD protocol has something like a distribution of quantum information. I mean, that's kind of maybe a very general thing, but let's say in the BB84 protocol, for example, this would correspond to Alice sending randomly random bits encoded in a random basis to Bob, or in the Eckert 91 protocol, this would correspond to the distribution of entanglement. Then usually you have something that I already mentioned, which is called parameter estimation. This is essentially the step where Alice and Bob trying to find out how many errors or how much corruption is there in the channel, or how many errors are there in the channel. Then there is usually a step that is called error correction or information reconciliation, where Alice and Bob try to eliminate errors in their correlated information they have. This is also error correction. These are essentially the same things, except that information reconciliation is slightly more general. So error correction assumes that, for example, Alice has the correct, so to speak, key, and Bob tries to correct the errors he has so that he gets the same key as Alice, or vice versa. Information reconciliation could be seen as something more general, where you say that Alice and Bob have some correlated information, and they want to end up with identical correlated information. But this identical one doesn't necessarily have to be identical to what Alice had at the beginning or identical to what Bob had at the beginning. So this is, in that sense, I use this term information reconciliation as a more general thing, but error correction is the usual way how this is done. And then there is usually a final step, which is called privacy amplification. And okay, we will not have to go into all these steps individually, but the point is that this is again similar to an aircraft. An aircraft has, of course, different components. It has wings, it has a navigation system, and so on. And the idea is now that we can analyze each of these parts individually and give a number, a failure probability for each of these parts. So we could say that each of these parts have a failure. For example, there could be already a failure in the distribution. This is usually not the case, so I will not write anything here. But then we have, for example, here a parameter estimation. So I call that epsilon PE. So this is, informally speaking, just the probability that my estimation of errors went wrong, that I got the wrong estimate. Then I could here call something like epsilon IR. This would be the information reconciliation. This would be, for example, the probability that Alice and Bob tried to correct the errors, but they fail in the sense that Alice and Bob, at the end of this phase, don't have identical keys without noticing it, for example. And then there's also the privacy amplification, which would be a failure of the type that you end up with something that has actually, I mean, you start the privacy amplification with something that has, in principle, enough entropy, but nevertheless, this hashing that is done in the privacy amplification gives you something that is not uniform. This may also happen. So in other words, I mean, from like a certain distance, you could say each of the components has a certain probability of failure, as in an aircraft. And what would you do in an aircraft to calculate the probability that it fails or that it crashes? As I said, you could just fly many times around in the world and see how often you crash. But this is not possible for a QKD system because we never know whether the adversary got the key. But the alternative thing would be to assess the safety of each component. You can try to see how often does it happen that the wing breaks off of the airplane, and how often does it happen that the engine stops to work in the middle of the Pacific. And then you can add these epsilons together, and it's clear that the total epsilon is certainly upper bounded by what people call the union bound, by the failure of the individual components. And this estimate is actually a very good estimate, because if these epsilons are small, then this number is essentially identical to the number if you would assume that all the errors occur independently of each other. So despite the fact that this is a worst case estimate, even if you would additionally assume that the probability of an error of the wing breaking off and the probability of an error of an engine failing are independent of each other, then you would still arrive at something that is almost like that up to quadratic terms. And the same is true for QKD. So this is essentially a formula where you don't lose anything. So that's the idea. So the idea is essentially add errors of the components together. Now I should make two remarks about that. So first of all, that this is actually allowed, that you can analyze these components individually and then just add up the probabilities, requires that you have a proper definition for what these errors mean. And what does it mean to have a proper definition what these errors mean? This means that you define each of these things in the same way as I defined here the error of the total QKD system. So you can, for each component, for example, for the parameter estimation, you can define kind of you can draw a box that, for example, takes as input the channel or the data and outputs the estimate for the number of errors. And you could draw the same box in the ideal case and see how often does the real parameter estimation you actually do in your protocol deviate from an optimal parameter estimation that you cannot do because you may not be able to test everything. But that would kind of give you always the right estimate. So you kind of always define these errors as a deviation from the perfect thing. And if you do that in the right framework, and that's why these so-called composability frameworks are used, then one can prove that it's safe to actually add up these individual errors. The other remark is that if we have additional assumptions, for example, if you only know that the parameter estimation works because you already assumed that, for example, the adversary doesn't corrupt the devices that do the parameter estimation, but you may not be sure that the adversary doesn't corrupt your devices, then you may have a probability in the assumptions. So you may have additionally some epsilon failure of the assumptions. So there's a probability of epsilon that would be that the assumptions fail. And then you could say the total probability would just add that. So essentially the whole framework is very generic. You just have to make sure you include all failure probabilities. And if you have derived these epsilons under the assumption that certain things hold, and that the fact that these hold are themselves subject to failure probabilities, you can add everything together. So that's the idea of these composability frameworks. Let me briefly mention that there are different frameworks of this type that are currently used. And just to give you these names, so one is called universal composability. And this is sometimes abbreviated as UC. And that's the framework that I mentioned that has been developed by Ranconetti and generalized to quantum mechanics by Michael Benor and Dominic Myers. And I think now there are some nice works by Dominic Unruh, where he developed actually a very clean theory of that on the quantum level. There's also something that I'm working on together with Uli Maurer, which is called abstract cryptography. And this is another framework which is somehow completely, it's supposed to be compatible with that one, but it's on a more abstract level. It's less kind of specific about how exactly you do your devices. It's kind of on a level where the actual realization doesn't matter so much. It's called AC, and this is by Uli Maurer, myself, and Christopher Portman, who is currently working on that as a framework. Okay, so this guarantees that you can actually define these things, but essentially what you have to know from, if you're not really technically working on that, is just that once you have the proper definitions, we can do this addition. Now this brings us to the point, how do we now evaluate these individual epsilons? So if I'm now, for example, looking at parameter estimation, how do I determine what is my epsilon PE? And let me just give one of, for parameter estimation, the analysis is relatively simple on a generic level. So I will just give you a feeling of what happens. How do these epsilons come about? So, okay, so as I said, the idea is that these epsilons quantify the probability of a deviation. What does a deviation of a parameter estimation mean? So what is parameter estimation? In parameter estimation, I have essentially the problem, which is, I could state as follows. I have, of course, Alice. And Alice encodes again in a certain basis, 0 or 1. And then it's sent over the channel, and the channel is somewhat noisy. And now I get a noisy version of 0 or 1. And one way to model the noise is by a binary bit flip channel. So I could say that if I have a 0, then with probability 1 minus epsilon, it ends up as a 0 on both sides. And with probability epsilon, it ends up as a 1. That's one thing that could happen, and the same for ones. So this is a binary symmetric channel. And now, of course, depending on the attack that Eve carries out, and depending on the noise we have in the channel, we will have different values for epsilon. And the idea of the parameter estimation is to determine this epsilon. By the way, I should maybe not call that epsilon here, because the epsilon is already needed for the error. So let me call that P for just the probability of a flip of the whole thing. Now, the security or the rate I achieve in the protocol will crucially depend on this P. For example, if P is 0, then I can assume that no disturbance has happened to my signal, which means that the rate is usually maximal. And for example, for BB84, so the rate I get, the key rate for the case of BB84, is essentially equal to 1 minus 2 times, this is the binary entropy function of P. So what is the binary entropy function? Let me briefly describe that. That's just minus P times log P minus 1 minus P times log 1 minus P. So this is just the entropy essentially of a bit with the probability distribution P and 1 minus P. So that's the rate you get. And now, of course, if we wrongly estimate this P, we will do the analysis or the privacy amplification and all that under a wrong assumption of what about the capacity of the channel, and this will lead to some insecurity. So if actually there is a large error here, but our estimation says P was equal to 0, then of course we will kind of assume that we can use all the bits that Alice sent to Bob as secret key bits, which will actually then lead to the fact that Eve knows certain bits if she actually disturbed the channel. So it's important that we correctly estimate this value P. Now, how do we estimate the value P? We just do it by statistical inference. We look at, so what Alice and Bob do in a protocol is they compare certain positions with each other. Alice says at position 7, I sent the 0 in the computational basis, and Bob says, oh yes, I received actually 0 at position 7. But they only do that, of course, for a limited number of positions. Otherwise, they would, of course, reveal the whole key. Now, by pure statistics, you can show the following, and this is essentially a Chernoff bound, which says that if you now do a comparison with a limited number of tests, so if you do k tests, then the probability that the estimate, so let's call the estimate est, is in the interval, in the correct interval. So what is the interval? It's P. Let's say we tolerate some deviation delta. So delta would be the deviation that we tolerate. I mean, the estimation will never exactly tell us what P is. It will tell us that P is roughly a certain value, and how roughly is characterized by this delta. So it tells us how well we approximate P. And now the probability that the estimation is in this interval will essentially be larger than 1 minus something that, there's some constant usually here, but that decreases like delta squared times k, where k is the number of tests. Now you see, intuitively, and this is also what can be shown, the failure probability of the parameter estimation is essentially the probability that the estimate is not in this set. So in other words, the failure probability, the epsilon parameter estimation, is essentially bounded by 1 minus this, because if it's not in this interval, so in other words, it's of the order of epsilon times a constant times delta squared times k. So this would be now a value that you get in an analysis of a protocol. Now what do you have to do as someone who analyzes protocols? So there are, of course, still many parameters. There's a delta and a k. And now you could say, this just means I can make the k very large. But if you want to make the k large, you, of course, lose key bits, because k is the number of bits that you use in order to do the statistical test, and you cannot use these bits later for generating your final key, because you have to reveal these bits towards Eve. So you want to keep the k small in order to make the rate large. And if you actually do a very rough analysis, you can say that the rate of a protocol is, of course, so if you have initially n signals that you exchange, so let's say n is the number of signals, then the rate of an actual protocol is now, this is now the rate prime. It's not this asymptotic rate that I had before. It's essentially given by n minus k, because that's what you lose, divided by n. And then you still have this expression from before, h of, and now, because I have only an estimate of p, I need to make a worst case estimate. And assuming that p is smaller than 1/2, the worst case is this. So this would be my new rate. And now, I told you at the beginning that getting a value epsilon is always a trade-off. So in this particular very simple case, I mean, usually there are more parameters, but in this very simple case, we have now two quantities, namely, or two values. Namely, we have this estimate for epsilon, which depends on k and delta, and we have the rate that also depends on k and delta. And of course, it also depends on n, the number of bits, and so on. Now, the goal is to make this, so if you want to make this here smaller, then this comes at the cost that also the rate is smaller. So you have to find a trade, you have to do a trade-off. Yes, Gilles?
Now, are you implicitly using Bayes' rule with some higher probability on what p is? Because what's at the bottom is what we really want, probability of failure.
Mm-hmm.
The middle line is the probability of the estimate. And you want to get p.
You mean here?
Not of the estimate, because of p.
You mean here? You're talking about here, but
What you get amount here is the probability of the estimate is close to p.
yes.
What we really need is that p is close to the estimate. It's not the same thing.
Aha, yes, that's right. Yes, this is a good point. So there is kind of, what we want is that, indeed, as I say, that, I mean, the probability, this p, is itself not a fixed value, because the adversary may choose it randomly. So I already made for this thing an assumption that p is fixed. Now, why can I do that? I would argue I can do this. And the reason why one can do that, I actually don't want to go much more into that, but the reason is essentially that usually we have another problem here. So that all the computations, not only for that one, also the computation here and the computation here for this epsilon will usually have to be based on the assumption that the channel behavior is fixed, that I have kind of a channel, that this channel from Alice to Bob, or it's no longer drawn, but the channel from Alice to Bob has a fixed channel model. This is, of course, never the case, because an adversary can change it. However, there is this, as you know, the Definetti theorem, which tells us that we can always assume it without loss of generality. However, as soon as we apply this theorem, we get another epsilon, which I wanted to briefly mention, which is kind of usually called epsilon df. So those who read papers about finite size security sometimes see such a term, and it's sometimes incredibly large. And the reason is that this Definetti theorem, which essentially tells us that the usual assumptions we make for the analysis, which is to have a fixed channel model, are only in the finite size regime valid, again, with a certain probability. So if we add this thing to it, then I'm allowed to think in that way. If I don't, then I'm wrong. And indeed, I will say that when I come to the outlook, making this actually smaller is one of the big challenges in the theory. Okay, are there further questions? Because that's essentially what I wanted to tell you about how. So I will, of course, one could now go through all of these things, and I could tell you for each of these things how we calculate the epsilon. I didn't do it for any of those, not even for parameter estimation, because what I told you now is just a very simplified example. Of course, in reality, you have to estimate more values and so on, but I hope I gave you just a convincing enough example that you see that the epsilon is usually somewhat exponential in the type of cost. So it's exponential in, for example, the number of tests we do, but there is always a trade-off that the larger I make this k, the smaller is at the end my rate. For example, you see that also in the delta. If you want to make the delta larger, this will of course make this thing here larger, but if this is larger, by the way, I forgot a 2 here. If this is larger, then the h is small, this bracket is again smaller, and so on. So this is how you get actual trade-offs between rate and security. And that's what I said is similar to an aircraft. So if you want to build an aircraft, you have to make a decision how secure should it be. And the more secure you want it to be, the heavier it will be, the more redundancy you need, the more fuel need at the end to operate it, and this is exactly the same for QKD. You have to make a decision. It's not just good to have an epsilon arbitrarily small, because you will end up with a very inefficient system. And conversely, you don't want to have a very efficient system with epsilon equal 1, because then you could just replace it by a random number generator on Alice and Bob's side. Okay, so this brings me almost to the end. I would like to, there's a question, yes?
Do you think that factor 2 is inherent or could be improved?
This factor 2 was just, thanks for the question, this was just for this very simple example of the standard BP84 protocol where I do not do any further optimization. The answer is yes, it can be improved, for example, by an asymmetric version of the protocol where you do the test only in one basis and you don't do any test in the other basis. And there are many ways to adapt the protocol to improve it. So this was just a toy example, essentially. Okay, so if there are no further questions, I come to my last thing here, so which is what next. And essentially, I should first of all stress that the whole analysis of quantitative security, somewhat surprisingly, has only started recently. But now I think almost any serious group who is doing QKD and has the technique to do finite size analysis has already realized that one, of course, has to make statements like that. Because as I argued at the beginning, otherwise it's not really a security statement. But I said now every serious group that has the techniques. So the problem is that we don't have the necessary techniques to actually calculate these epsilons for all type of protocols. And for a long time, for example, we didn't have any reasonable technique for the case of continuous variable protocols. There has recently been some substantial progress, among others by people in France, among them, for example, Anthony Leverrier, who have actually come up with ways to calculate these epsilons, even in the case where we have continuous variables. However, as I mentioned before, as an answer to Gilles' question, we have certain techniques that are used in security proofs, like the Definetti theorem, which, when you do a finite size analysis, add enormously large terms to the whole thing. And there were also some improvements. There's something called a post-selection technique, and there are other ways to improve these things. But the problem is still that if you take a generic protocol, you usually have terms that come in from kind of by the fact that our techniques to prove security still make huge detours. Because, I mean, despite the fact that I'm myself kind of introduced this Definetti theorem, I would say it's kind of a detour. I would hope that once we have a better understanding of security proofs, we will kind of not need to make the detour via Definetti. Definetti is kind of a way to make the thing nice so that we can use the established information theoretic techniques. So in some way, one could say information theory has been developed for IID distributions, probability distributions and states. And everything we know works well if you have states of the form rho tensor n. And Definetti is a technique to reduce everything to this nice case. But the more direct way would be to actually develop techniques that are directly dealing with states which don't require this structure. And then we don't need Definetti, and we would not need to have a step in our analysis which adds huge epsilons. And this is currently being done, and I think we will hear more about that, also within even this conference, I guess, or actually in the next talk. There's a talk which presents work by Thomas Michel, Martinez Matteo, Pacher, and Corona. I think he will be the last one will be the speaker, where we will hear more about techniques to actually bound these epsilons, and also in the talk after by David Suter, we'll hear something about the efficiency of post-processing. So making these parameters small is currently a huge effort in the theory community, but there is a lot to be done. So if sometimes people say, what do you actually do when you do quantum cryptography? You already know it's secure. The point is, no, actually we don't, because usually the values we have for the epsilons are just too large to be practically relevant. So for most protocols, the question whether we can achieve a value of epsilon which is in the useful regime is still largely open. And this is particularly true for new types of protocols, like, for example, device-independent protocols, where we have a complete lack of techniques for finite size security. There we are still fighting with security in the infinite size regime. And the work to actually do the whole thing in a practically relevant regime so that we get epsilons that are reasonable has not been done. So this means that I would encourage the young people who don't know yet what to do, that this is still an open field. So they shouldn't think everything is now solved. Actually, I would say there are even more open questions than we thought some years ago, because some years ago we were not really aware of this finite size issue. Now, what are other, so first thing is, of course, in some way you need to do the hard work and actually look at these things and develop better techniques and maybe avoid this sidestep through Definetti. The other thing is, and I mentioned that before, again at the example of the aircraft, it's not so much a for example, an aircraft can fail in a different way. The navigation system may fail and the aircraft may land at a different airport than its destination, which sometimes happens. But this is not so bad as a crash. And you could say if the epsilon that the aircraft lands at the wrong airport is maybe just 10 to the minus 3, you would still fly, you would still take aircraft as your means of transport, whereas if this epsilon would apply to the probability of crash, you certainly wouldn't. Now, the same is true for QKD. We had before different types of failure, and I said before that, for example, one type of failure is that the adversary learns information about the key. This is certainly something we want to avoid. And because we don't even notice it, we want it to be so small that we don't need to care about that event. But there's also a failure, for example, if the key that Alice has and the key that Bob has do not agree. And if this failure is relatively large, we wouldn't usually care, because this would just result in a communication later in some, would result in a wrong communication. So it would just mean it's like a noisy channel. So if you generate the key and then do one-time pad encryption with a key where Alice and Bob's key deviate, this is as if we had some noise in our channel. And because in practice we anyway correct for noise in the channel later, or would send a data packet again if it doesn't arrive, we don't really mind whether this probability is large. But this would mean that, for example, because the probability that you have a deviation between Alice and Bob is essentially determined by this, and the probability of secrecy is determined by these two. So we could separate these epsilons and have some epsilons which we could allow to be large, which would make our scheme more efficient. Because the larger we can make certain epsilons, the more efficient we can make our schemes. So conceptually, this would mean the following, and this would be my last little thing I want to say, that we have, we could think of several ideal devices. So on the right-hand side, I just drew this real and ideal one. And now we could say, why don't we split the ideal one into several parts? This is, by the way, not a new idea. This has been used already in the past by several people that said that, but let me just phrase it in terms of these ideal systems. So we could have an ideal system that I call secret and an ideal system that is correct. So the ideal secret one would be one where I get some key out at Alice's side and SB on both sides, and I have nothing going to Eve. I mean, I would also add this red stuff, but I don't draw it now. But we have only the requirement that no leakage to Eve. But it could be, so SA may deviate from SB. So this is, of course, not what we want, but then we could have a correct system where we have SA and SB, and we have the guarantee, but some information may leak to Eve. So here we have the guarantee that SA is equal to SB. And now our requirement would be that our real system, so the requirement would now be that the real system is epsilon close to the secret one and epsilon close to the correct one. So the requirement, let me write that in black, the requirement on the real system is that we have epsilon correct close to this system ideal correct, and the second requirement is that it's epsilon secret close to the ideal system which is secret. And the idea is now that epsilon correct may be much larger than epsilon secret. And this gives us, so epsilon correct could, for example, be 10 to the minus 3 and epsilon secret 10 to the minus 9. And by making one epsilon larger, we get more freedom in the choice of our parameters and can therefore make our scheme more efficient. So that's one way to actually make the things much more practical. And you could, of course, invent different distinctions and say maybe there's, you, for example, distinguish between a little bit of leakage to Eve and a lot of leakage to Eve. For example, if you have an application where it's never a problem if only one bit leaks to Eve, then you could define that. But I wouldn't, by the way, expect that this gives you much advantage. But clearly to separate the correctness from the secrecy will buy you a lot, because it's very hard actually to devise error-correcting codes which are correct with very high probability. Of course, you could do some tests and so on, but this all costs, and you may reduce the costs by such distinction of tasks. Okay, so this brings me to the end. I would like to just briefly summarize my main point. And my main point is really that without giving a number epsilon, you haven't really made a scientific statement. Okay, thanks a lot for your attention. And
concerning the thing you said last, with separating the secrecy and the correctness, in cryptography and the security of multi-party computation, this was something how it was done in the very early definitions. And there are some cases where it's known to go wrong, so where they are separately satisfied, but things go very bad if you put them together. So I don't have the feeling that this is actually happening here, but is it known that if we, for example, ask those two things separately, that we really get something good, like the normal security with the minimum, the maximum of the epsilons, or something like that?
This is a very good point, because it's indeed true that if you compose such statements in a too naive way, they often go wrong. Now, in this case, there is actually, for example, one thing that could very easily go wrong. For example, if I would here define the leakage to Eve as only the leakage regarding the key SA or SB separately, but Eve may learn something about the correlations between the two, then indeed it can go wrong. So the answer is essentially, I have to really think hard to do this properly, to define that system properly. And I haven't, to be honest, I haven't done this formally, but I thought a little bit about it, and I think if one does it properly, one can avoid the problems, but one really has to actually, as you say, be very careful to say what one exactly means, because now I'm actually talking about two variables which may be different, and I have to define what it really means. And I have to make sure Eve has no information over the joint variable SA, SB. And naively, one would probably maybe just have defined she has no information about SA or SB. So yes, one has to be very careful, but I think because it's purely information theoretic, these things usually work. As soon as it would be computational statements or more parties with... Yes, I mean, yes, there's also, if you have, for example, different adversaries, here the adversary structure is kind of fixed. So these are things that make such considerations usually easier. But yeah, so I think it should work in this case, but I'm not aware of a work where this has actually been done formally.